cardiac muscle cells will release atrial natriuretic hormone if they're stretched too much. And that comes from your blood volume too high and your blood pressure too high. And we already said that's going to lead to increased water loss. What it does is it does two things. First of all, it reduces in the distal convoluted tubule sodium recovery. Less sodium recovery means you recover less water in the distal, the distal convoluted tubule. It suppresses ADH suppression, directly suppresses ADH. No ADH is produced, therefore in the collecting duct, you're not going to be recovering any water. You're going to produce a large volume of dilute urine. Everybody follow the sequence of events? Those of you that came in, if you do not have chapter 26, part 2 notes, they're up here. And you are Chad, right? And I have your test report while you're here, right there. Trevor, you have yours. Yes, you do.
Dr. Noni, would it be possible to maybe start 2 slides before this? It was kind of rushed there at the end of the last
Was I?
class,
Okay,
and we
let's go
really
back.
didn't cover it very
Reduction of concentrated urine?
Yeah.
Well, aldosterone does a little bit. What aldosterone does is target distal convoluted tubules and causes increased sodium recovery. Okay, ADH. When ADH is secreted, it's, again, it's secreted primarily because you have increased osmolarity. That means in the fluid outside of the cells, less water. So the concentration of solutes goes up, okay? So the osmolarity goes up. And that ADH is going to bind to receptors in the basal membrane of the distal convoluted tubule and the collecting duct. And it's primarily in the collecting duct it has its effect. Now, when ADH is secreted, it's going to bind to receptors, and they're going to put aquaporin molecules into the apical surface and the basal surface of the cells that line the collecting duct. Now, ADH's primary effect is on the collecting ducts. Only a little bit occurs in the convoluted tubule. Now, the convoluted tubule is sitting in the cortex, and now it's true that the interstitial fluid around the distal convoluted tubule is at 300 milliosmolar. There is some water loss there. But as that then goes through the medulla down the collecting duct, it's going to go to much higher. So this is 100, and it's going to produce a urine that's about 1,200 milliosmolar. Because as that fluid is going through, we have all these aquaporin molecules in the membrane, apical surface and the basal surface, so water is coming out. Because every bit it drops, it goes to a much higher osmotic concentration around it. We have formed this gradient by the urea and the action of the loop of Henle, so you can then do this. The whole purpose of the medullary gradient is so you can then produce a concentrated urine to conserve water. If the blood pressure is too low, the blood pressure is too low, osmolarity too high, you'll release ADH and you're going to pull water out all along that collecting duct. There is some lost up here, but not near as much as is lost in the collecting duct. Okay, because it's only 100 to 300. Here we're going to have it exposed to much higher concentrations. And it comes out at about 1,200 milliosmolar. This is as concentrated as you can get. Noel, do you have chapter 26, part 2 notes? Didn't think so. Here's the copy for you. Okay, did that cover a little less quickly? Do they? Okay. Which hormone do you think has the biggest effect on the composition and concentration of the urine? Aldosterone or ADH? Which one do you think is the biggest? Yeah, ADH by far, because it's pulling out a lot of water. You don't have a lot of sodium to pull out up here by aldosterone, but it does. Blood pressure's low, you'll secrete renin, angiotensin, aldosterone. You will pull out some sodium, and as a result, water will come out, but you don't get near as much water as you get right here. Okay? When ADH is not present, all of those aquaporin channels are non-existent, and as it goes through all this collecting duct, even though it's a much higher concentration out here, there's no aquaporin channels, so water can go out. The difference is no aquaporin channels and aquaporin channels. ADH causes them to be put in, and ADH is a water conserving, you can see it right here, a water conserving hormone. Okay? Any other questions, Lisa? Fat ADH, large volume. Now, it doesn't matter whether you pull the water out or not. All of those wastes that are in here are still gonna be in here. Pull that water, it's in there. Don't pull that water, it's in there. So, the whole purpose of this water conserving process here is in case you are dehydrated and your blood volume is low. We're gonna recover water. You don't lose as much. What happens if your blood pressure is high? Well, that's the next slide. Okay? If your blood pressure is high, you're gonna secrete atrial natriuretic hormone or peptide. And it does reduce sodium absorption. It does reduce water recovery by reducing sodium reabsorption, but it totally suppresses ADH. Now, ADH is a small peptide hormone. It's lost from the blood quickly. We already went through and said the very smallest proteins can get out a little bit, but these short peptides, the short peptides, the ADH is a peptide hormone. It gets out really quick, so it's removed from the bloodstream very quickly.
So from one void to another, it's already changing.
Yeah, yeah. Once you end up with too much water volume, too much water in your blood, you're gonna quickly suppress ADH secretion and lose a whole bunch of water, bring your blood volume down, bring that blood pressure down. The whole reason this is secreted is because blood pressure is too high, because your blood volume's too high. Okay? And this causes you to produce a large amount of urine. And of course, ANH is going to cause widespread vasodilation. Any questions on that? Pretty straightforward? Okay, let's go and talk about some measures of renal function. So we're going to talk about plasma clearance, tubular load, tubular maximum. First, we're going to look at plasma clearance. It's the volume of plasma that is totally cleared of a substance in 1 minute. Now, what volume of plasma is cleared, what volume of filtrate is formed every minute? 125 milliliters. If you clear half of that, then it's 62 and a half. If you clear half of a certain compound from that 125 milliliters, you're clearing really totally cleared 62.5. If that's what happened. 62.25, 62.5, that's right. Okay? Plasma clearance. You can calculate plasma clearance by taking the volume of urine produced milliliters per minute, concentration of that entity in the urine, and the concentration in plasma. if you know those, though, all of those, you can calculate plasma clearance. Milliliters per minute, concentration is so much per milliliter, concentration so much per milliliter. They cancel out. You're clearing a certain milliliters per minute. These two cancel each other out as far as units go. So you're clearing a certain volume of plasma per minute. Now, of course, that plasma has to go into a filter. Okay? If a substance is not reabsorbed, and if a substance is not reabsorbed, the concentration in the urine equals the concentration in the plasma, and you end up with a measure of GFR, how much urine is produced. I mean, you end up with GFR, that's milliliters per minute, is going to be, end up having that, because it's going to be lower in the urine, actually, than in the plasma, but this ratio is going to be related to GFR. If a substance is not reabsorbed, it goes into the filtrate, cannot be reabsorbed, then this formula will produce GFR. Okay? Tubular load. Tubular load is simply how much of a substance enters the filtrate every minute. Okay? What's the actual quantity of a substance entering the filtrate every minute? So if you have a certain amount of a substance in your plasma, there's a certain amount that's going to enter the filtrate every minute. That's not something that's used by itself. It's used with the tubular maximum. The tubular maximum is the amount of substance that can be reabsorbed every minute. Now, how much can be reabsorbed of a substance depends on the substance. Some are reabsorbed very high, some in the middle, some very low. Every substance has a tubular maximum, the amount that can be reabsorbed as it goes down the proximal convoluted tubule. Down the rest of the tubule, there's no reabsorption. So for glucose, the maximum amount, the tubular maximum is, hate a vibrating phone. Okay, tubular maximum is the amount of substance that can be reabsorbed. That's a certain quantity, okay? So, for example, for glucose, I believe the tubular maximum is 180 milligrams per liter. I think about 100 milliliters, okay? If you have let's say your plasma concentration is 120. You've just had a meal and it's gone up to 120. Can you recover all of that? Yeah, because 180 is the maximum you can reabsorb and only 120 is coming in. Got it? If you have diabetes, you can have up to 200, which means you absorb 180 of that, the 20 goes into the urine, you end up with glucose in your urine. For most normal individuals, the tubular maximum is so high that those substances are completely reabsorbed. If something's wrong with the tubular or something's wrong with the concentration, you can end up with that material ending up in the urine. So if the tubular load, which is the previous one, is too high, is higher than the tubular maximum, you end up with that substance not being fully recovered from the filter, okay? And this is only important in things like diabetes. There's not much else that can happen to cause other entities to go into the urine. But if the transport processes are defective for some reason, then you can't obviously reabsorb it, okay? The tubular lobe is greater than the maximum. The excess is going to go into it. The urine. Urine movement. This is fairly straightforward. Let's go and go through here. We know that hydrostatic pressure generated in the renal corpuscle is going to push fluid through. Now, the actual rate of fluid movement is pretty fast in the proximal convoluted tubule, but as you pull full water volume out, it becomes slower and slower and slower. Okay? Once you reach the renal pelvis, there's no pressure there to push the urine any further. In the ureter, there are periodic peristaltic waves that move down the smooth muscle and move the urine out of the ureter into the bladder. So the human urinary system works fine for urine movement in zero gravity because we don't use gravity to move urine into the bladder. Okay? So there's peristaltic waves that do that. So hydrostatic pressure gets it to the renal sinus, and then peristaltic waves down the ureter moves it into the bladder. Now let's talk about the micturition reflex. And there's a small little error, and it's something you can ignore in the book, really. When you fill the bladder, there are stretch receptors in the smooth muscle of the bladder that report how much urine is in the bladder. Once it reaches a certain level of stretch, it's going to send an impulse. This is the stretch receptor. Here's the sensory receptor. It's going to send inputs into the sacral region of the spinal cord that your bladder is getting full. It's not saying it's really full. It's just saying it's getting full. Okay? It's going to say it's getting full, and then if you ignore that, it'll tell you later it's getting fuller, and then a little later it's telling you it's fuller, and then later, you know, you're dancing and running. Okay, so in the sacral region of the spinal cord, when it receives that sensory input, it's going to send an input to the smooth muscle, telling it to contract. Okay? And it's going to cause the internal sphincter to relax. Now, if you are an adult, the book says external sphincter, but it's really the internal sphincter that's told to relax. If you do not have control of the external sphincter, which is a skeletal muscle, the smooth muscle, then urination occurs right then. If you have no ability to control that muscle, there's no motor tone, and you will have urination. So that's an infant. The diaper is now wet. Okay. In an adult, the internal is relaxed, but the external has muscle tone and urination does not occur. If this actually relaxed the external sphincter, you would urinate at that time. Okay. In an adult, at the same time that it receives that stretch, the stretch information, it's going to send impulses up to the pons, right there. That's the pons. And then that sends impulse to your cerebral cortex, you becoming aware of your bladder getting full. Now, if you're an adult, this external urethral sphincter is already contracted, no problem, nothing happens. Okay? It may stretch some more and send impulses again and tells you again it's getting fuller. Okay? That can happen several times. Okay? Whenever it's convenient, then you use conscious commands to stimulate the sacral region that will cause the internal to relax and the external to relax, producing urination. Yes?
How does when you have an enlarged prostate, what pressure gives the blood, does it push up?
No. What's happening is in the male, right here, we have the prostate gland. If you have an enlarged prostate, it's compressing the part of the part of the urethra which goes through the prostate. The prostatic urethra is compressed, and this muscle has trouble generating enough force to get it through that small opening. Dribbles out. Okay? If you have an enlarged prostate, you need to get that fixed, if that is the question. And first of all, you need to get it checked. Is it due to a tumor, or is it just getting old? Okay? It does swell. Yes?
I heard you can get an infection from not releasing your bladder, is that true? Or holding for a long time?
No. The only way to get an infection is bacteria have to come up through the urethra. Now, a male, that's much longer and rarer. So frequent urination, if there is bacteria that get in, frequent urination is gonna wash them out. Okay, for a female, it's much shorter. And they're much more prone to urinary tract infections, UTIs, than a male. Okay? Unless you are very dehydrated, you're urinating average enough every day to prevent that from occurring. If you make yourself really dehydrated, so you're really producing small urine, urinating once a day, you might get yourself to be able to have, even in a male, a UTI. Okay, but, I mean, bacteria, the only way they're gonna get here is coming from the outside. In a male, they have a long way to go. If you have frequent urination, it's washed out. Female, much shorter, much more problems. Okay, in an adult, it's conscious commands that cause the smooth muscle, the detrusor muscle to contract, and the external urethral sphincter to relax.
Is incontinence an issue with the sphincter?
Incontinence can happen if you have less and less, the only way it can occur is less and less control of the external sphincter. If this is compromised, then you have incontinence. The internal urethral sphincter can fail, but if this one is still working well, you shouldn't be incontinent. It has to do with the external as far as I would guess. Because that's the one you ultimately have to relax. The internal can relax and it's no big deal. Okay. We are finished with chapter 26, part 2. There's a couple of questions, and we will move on to chapter 27, which is really applied chapter 26. That's really what it comes down to. Okay? We're now going to look at how the kidney works. It maintains water, acid-base balance. Another fun one. Okay. Thought I would stop getting these after the election. Unfortunately, still getting crazy calls from Minto, North Dakota. I don't even know where that is. What effect would increased amounts of aldosterone have on potassium concentration in the urine? It would cause more potassium to be secreted, therefore it would go up. And there is a chart. There is a chart that shows secretion, and we're talking about hydrogen ion, and over here's the proximal convoluted tubule, over here's the distal convoluted tubule, and there is a sodium and potassium. You're gonna bring the sodium in and put the potassium into the urine. That, I told you, was stimulated by aldosterone. Next to it was the sodium in and the hydrogen ion out. So you go back to that diagram, I said that one, I pointed out, that one right there, stimulated by aldosterone. So, aldosterone is secreted when blood pressure is low, and you're trying to absorb sodium to have water follow it. And to do that, you have to exchange it for potassium that increase the potassium concentration. If you're running a lot of that, you don't have enough sodium to put enough hydrogen ions out. Okay? So, this will increase your potassium ion concentration in the urine. Next question. How would the lack of juxtamedullary nephrons affect the volume and osmotic concentration in the urine? If you didn't have enough of these nephrons, just a bunch of cortical ones, what could you not do? You could not conserve as much water when you need to, because you can't build a big enough concentration gradient to pull water in and conserve it when blood pressure is low. Okay? So your urine would not be as concentrated, would contain too much water. Okay? You couldn't produce concentrated urine. If you don't have enough of those nephrons, you can't produce as concentrated urine. If your gradient only goes down to 600, you pull out a lot less water. Okay? You couldn't produce nearly as concentrated of Chapter 27, Part 1. Chapter 27 is applied chapter 26, really is what it is. We're talking about fluid homeostasis. Does the kidney have anything to do with fluid? Yeah, we're talking about losing or recovering water, right? Electrolyte. Are there electrolytes that are taken in by the kidney? Yeah. Acid base. Yes, those hydrogen ions have to do with acid base. So this is really looking at the kidney. Now, we're gonna look at other parts of the human anatomy and physiology also, but we're primarily gonna focus on what the kidney does. Learning of outcomes. Identify some major fluid compartments of the body and their subdivisions. We're going to take the human body and divide and talk about various compartments of fluid. List the dominant anions and cations in the major body compartments. Do our body fluid compartments differ in their ion concentrations? Yes, and we'll see that. And you probably know this already. Describe the causes of edema, leaky capillaries. There you go. Explain how water content of the body is maintained. If your fluid concentration is too high, what do you have to do? Lose some fluid. Fluid concentration is too low, osmolarity too high, you're gonna have to bring in some more fluid to lower it. Explain the mechanisms that regulate extracellular fluid volume. Describe how intracellular fluid composition is maintained. Do we directly maintain intracellular fluid composition inside the cells? No, that's up to the cells. It's really only up to the cells, because they determine what they bring in. Now, can you be so dehydrated you pull water out of cells? Oh yeah. So we can affect it a little bit by taking the interstitial fluid around them and adjusting their concentration. Discuss how sodium ion concentration is achieved. Describe the regulation of chloride ion. That's an easy one. It's regulated right along with sodium. Explain potassium ion homeostasis. Demonstrate an understanding of calcium ion homeostasis. We've covered that before in chapter 6 on bones. Regulate the mechanisms governing magnesium ion concentration. Explain the regulation of phosphate ions. Describe the causes and symptoms of abnormal plasma levels of selected electrolytes. So there's going to be tables for these electrolytes that tell you the causes of abnormal concentrations of those electrolytes and the symptoms of them if you have abnormal. They're interesting to look at and you should be aware of those. Then we begin acid bases, demonstrate an understanding of acids and bases and their relationship with buffers, okay? And I will cover buffers in case you didn't get it first time through in whatever chemistry course you took. Explain the actions of the 3 buffer systems of the body. There are 3 buffers in your body, and they work to maintain the pH of fluids in your body, and they work well. Describe the mechanisms of acid-base balance. Explain the causes and effects of acid-base imbalances. There are 4 cases of acid-base imbalances based on their causes, and we'll talk about the causes and effects of those. pH is extremely important. Your pH of your blood has to be within 0.05 of a pH unit of normal. I mean, you can't get very far away from normal. So acid-base balance is extremely important. Okay, now, fluids make up a large part of your body. 50% of the weight of a female and 60% of the weight of a male is actually water. Now, why is there more water in a male than a female? Not because we drink more, not because we have a larger blood volume. Why is it larger in a male than in a female? No, we're talking about percentage. You can take a small male, equally sized female. Female has less water than a male. Muscle mass? Males tend to have more muscle. Muscle contains a lot of water. What do females have a little more of than the average male? How much water and fat?
Not
Not much. So the differences in the relative amounts of muscle and fat make up the fat and cause females to have less water than males per body weight. Just differences, okay? Now, so total body water, look, in 60% for males, 50% for females. Why so much in an infant? They just do. Even though they have a reasonable amount of fat, they have so much fluid in their tissues. We get kind of dehydrated as we get older, I guess. Now, we're going to look at the fluid compartments in just a second, but the fluid, major two compartments, inside of cells, outside of cells. Outside of cells, we have plasma and interstitial fluid, and there is some very small compartments outside of that that are regarded as insignificant. So let's look at the composition of these fluid compartments. We're going to look at inside of cells, interstitial fluid, and plasma. We're going to look at those, the ionic concentrations of those. Which of those is the largest one as far as volume? Inside of cells. And interstitial fluids bigger than plasma. So that's a given, but we're just going to look at the composition. So, I'm going back the right way. So here's plasma, here's interstitial fluid, here's inside of cells. What is located between these two compartments? Fluid inside the blood vessel, outside the blood vessel. What's between it? The blood vessel wall. What doesn't go out of blood vessels from the plasma? Proteins. So you would expect most of these to be very close, right? Until we get to proteins. See the difference? Most of these are very close. So plasma and interstitial fluid are very close in their composition except for proteins, 17, 0.0. See that? Now what's located between interstitial fluid and intercellular fluid? What's located between the fluid outside of cells and the fluid inside of cells? Plasma membrane. And the plasma membrane causes the difference between those two compartments. Between these two compartments, we've got the capillary wall. And proteins don't get out, so that's only the major difference. Everything else is virtually identical, isn't it? Okay, between these two, we have the plasma membrane, and there is where we will see the plasma membrane cause big differences. Sodium, 145 outside, 12 inside the cell. That's a big difference, right? We didn't see anything like that except for proteins, which simply couldn't fit through the little gaps. Potassium, 4.1 outside, 150 inside. That's the plasma membrane. 3.4, 4.0. Now, inside of cells, they're counting also what's in the sarcoplasmic reticulum. If you remove the sarcoplasmic reticulum, this is like less than 1. Okay? They're taking the entire inside. It's not in the cytosol. If you did the cytosol, it would be less than 1. Much less than 1. Okay? Magnesium, 1.3, 3.4. Big difference. Chloride, 118.4. Bicarbonate, a little higher outside than inside, but it's significant amount inside. Phosphate, 2.3, 40, because the cell brings it in. Protein, of course, is going to be much higher than outside. And other ones, the other anions would be more phosphates. Thought phosphates made up most. Oh, these other anions are the proteins. They contribute part of that. And the phosphates are part of it. Well, you can see that we have equilibrium and equilibrium, but there's a larger number of ions inside cells than outside of cells. So, understand there are barriers between them that cause the differences that we see. And of course, the biggest one is going to be the cell membrane, which causes all of those big differences. You don't have to memorize these. you probably already know. I refreshed your memory about the protein. Okay, now, your body fluid is held in two large compartments, fluid inside of cells and outside of cells. The fluid inside of cells is the intracellular fluid, okay? About 2/3 of all the water in your body is inside of cells. About 2/3, okay? That would tell you that this compartment inside of cells is about twice the size of the extracellular fluid. It's about twice as much, okay? In the extracellular fluid, we have two large compartments. We already looked at that. Interstitial fluid, fluid outside of cells, around cells, and plasma. And the interstitial fluid is much larger. 80%, 3/4 of the extracellular fluid is outside of cells, and the plasma is only about 20% of the ECF, okay? These two together make up virtually all of it. There are other subcompartments of extracellular fluid, but they're very small, very small. Lymph, cerebrospinal fluid, synovial fluid, the endolymph in your inner ear, the perilymph in your inner ear, aqueous humor, and the vitreous humor in your eye. These are very small compartments, okay? So these are usually excluded when we're talking about the extracellular fluid because these are the major compartments. So the major compartments we're gonna work with are intracellular fluid, extracellular fluid, those are the big ones. And extracellular fluid is made up of interstitial and plasma. Understand their ratios, okay? For example, can water cross the plasma membrane? Yes, osmosis. So if you're dehydrated, so this volume goes down, where are you gonna get water from? Will water move by osmosis from inside of cells outside? Yes. Now understand, if you lose 100 milliliters of this fluid, you'll have 100 milliliters, a little less, but 100 milliliters approximately come out. Now that's a big part of this, but it's not as big a part of that. So you can do that. You can have water move from inside of cells out by osmosis. If you drink a lot of water, will water go from the excess go from here into cells? Yes. And you read in the introduction, you can actually drink so much water, you can put enough water in there that those cells don't work right and you could die. Okay? Because water, getting between these two is the plasma membrane, and water moves in and out of cells by osmosis. You get so dehydrated that eventually you can die. Not because you don't have enough of this, but because you pull too much out of there. Or you can drink too much that you can damage your cells that way. Okay, ECF subcompartments have a significant water and ion exchange. Why is there a lot of ion exchange between them? Where they go through capillaries, going through, they have a large surface area. Remember, we have 10 billion capillaries and capillary beds. That's a huge surface area. So water can leave the plasma and go into interstitial fluid. Water can leave here and go into there quite easily, okay? Whenever you have increased capillary permeability, for whatever reason, you're going to have edema. So increased capillary permeability or increased hydrostatic pressure. Blood pressure goes up. You're standing up and you have a higher blood pressure in my feet than I do back up here in my body. I'm going to have edema where? Down there where you have increased hydrostatic pressure. And how can you solve that edema forming in your feet? Walking, using skeletal muscles, pushing the blood up and recovering some of that water. Yeah. Okay, everybody, any questions on the two compartments, the movement of fluid between them? Okay. Regulation of body fluid concentration and volume. Are those two related? Yes. So let's go and look at it.
Regulation of the water content in your body. Your body wants to keep the water content of your body, how much water is in your body, constant, okay? What's one reason it's got to be held constant? If you have too much water, what builds up in your plasma? Water. What does that do to blood pressure? So the hidden reason behind you have to keep it constant is for blood pressure. Okay? Too much water, too much blood pressure. Too little water, too low of blood pressure. The body keeps total volume of water constant by keeping water gain and water loss equal. When you are getting less water, what is your body gonna do? If you're gaining less, you lose less. If you're gaining too much, what does your body do? Lose more. See how those are kept? Your total volume is kept constant by regulating how much you gain and how much you lose. If you've lost too much water, what happens to water gain? It goes up. We'll see how you do that. It's a simple concept, it's called thirst. Okay, when the water volume of the body is altered, it changes solute concentration of body fluids. Is that being monitored? Yes, in the hypothalamus, in the around the neurons that release ADH. It changes blood volume and blood pressure. Is that being monitored? Yes. And also, it changes interstitial fluid pressure. And okay, water gain, by the way, if you would like to know, 90% of the water gain comes from ingestion. We do make water every day in our mitochondria. About 10% of the volume of water we take in we need every day comes from metabolic water made at the final electron acceptor of oxygen. It makes a water molecule. So that's 10% of the water. That's constant. Does it ever change? Does that ever change? Yeah, if you're active and needing more ATP, then you'll run more aerobic metabolism and you can generate more water. Increase your metabolism, you will generate more water. Okay, water is lost primarily, the biggest place you lose water is urine. You lose 4% in feces approximately and 35% by evaporation. Is that just sweat? No. Can you lose water out of your skin not going through a sweat gland? Yes. Where else do you lose water? Tears, mucus, bigger than that. Respiratory system. When you breathe out, remember the air going in is dry, picks up water, and we're exhaling that? Yeah, that's the water. Okay, let's go on. Water intake is regulated by regulating your thirst. If you have high blood pressure, too much water, you're not thirsty. If your blood pressure is down, your water volume is down, you're really thirsty, okay? Neurons in the supraoptic nucleus, we already looked at that, are the ones that are measuring not how much water you have in your body, but it's going to be measuring the extracellular fluid solute concentration around those neurons. Those neurons are measuring the osmolarity of the water, of the interstitial fluid around them. Too much solutes mean you have too little water. Got it? You lose water, comes out of the interstitial fluid, and okay? And the major stimulator of ADH release is that osmolarity. Can blood pressure also stimulate ADH release? Yes, but it's got to drop a lot. It only has, the solute concentration only has to go up a little. Okay? Now, this is going to directly cause you to be thirsty. Just the osmotic concentration going up. Now, that's going to cause ADH release, but those neurons are neurons. They're connected to other neurons in your body that tell you you're now thirsty. What are you going to do when you're thirsty? Go drink some. Okay. We have baroreceptors that are measuring blood pressure. okay? We talked about those baroreceptors and carotid body and the aortic body. And whenever they detect a decrease in blood pressure, guess what you feel? Thirsty. Next, we talked about, they're continuing to call me. When blood pressure's low, you're gonna release renin. That's going to cause angiotensin, okay? Angiotensin, it's gonna cause angiotensin 2 to be produced. That is a stimulator of thirst. Isn't that crazy? We got all these stimulators of thirst. And generally, when you feel thirsty, it's all of them working. Because when you are dehydrated, blood pressure is gonna be down, extracellular fluid concentration around those neurons is going to be up. And low blood pressure is gonna release angiotensin. We got 3 stimulators of thirst. And when you're thirsty, you have that dry mouth because saliva secretion is reduced. And I mean, all of these work together. They're very strong. You're gonna be just focusing on finding some water. Okay? So, water intake is regulated by regulating whether you're thirsty or not. If this extracellular solute concentration is normal, if blood pressure is normal, and if there's no low blood pressure, no angiotensin 2, that's not gonna be around, you're not gonna be thirsty. Okay? Drinking fluids. Now, when you are thirsty, you go and drink some fluids. Now, you don't just drink a whole bunch. What you do is drink a little, thirst subsides for a minute or 2. If you drink enough, that's it. You don't feel thirsty anymore. If you drink enough, but not enough to meet 1 or all 3 of those, you're gonna be thirsty again and take another drink. You keep doing that, drink a little bit, I'm still thirsty. Drink a little bit more, a few minutes later, I'm still thirsty. You keep doing that until you have drunk enough water to solve 1 or 3, whichever one is causing the thirst. When you get your blood pressure enough, or when you get the extracellular fluid solute concentration down enough, then no more thirst. Yes?
I would say you should drink like 8 glasses of water, or should you just drink till you're not thirsty?
It doesn't matter how you do it, because if you ever have low water in your extracellular fluid, what are you gonna feel? Thirsty, and then go drink.
So you shouldn't drink when you're not thirsty?
You can drink if you're not thirsty. What happens if you drink too much? You're gonna pee. It's gone. Get it? It doesn't matter. There's some people walking around with gallon jugs of water they drink all day long. Go for it. They never feel thirsty, but they gotta go all the time. Your body will regulate your solute concentration. I am one that just drinks when I'm thirsty. Okay?
Does your body, and it goes to like the 8 ounces a day and everything. People that don't like water don't drink enough water in a day, but they're getting liquids from other places. Your body over time adjusts to the input that you're putting in.
Yeah, now, your water comes every day from what you ingest and what you make. Now, if you say they don't drink enough water all day, then what are they continually?
Metabolic.
No, they're continually thirsty. If they don't drink enough water every day, they're gonna walk around thirsty all day. Now, I don't know about you, but if I'm thirsty, I'm gonna find something to drink. What about you? You don't?
I hate water.
You hate water.
But you drink other things, right?
I drink other things, but at
There
the
you
same
go.
time.
Here we go, here we go. She's drinking, she's satisfying her thirst.
But does your body make adjustments?
No, it can't. This is built-in physiology. You can't be perpetually dehydrated because you're gonna walk around always thirsty. Really. So if you're not thirsty right now, it's because you have drunk enough water. Now, you may be producing ADH all the time, but you're still gonna be satisfying the thirst.
Can it be any form of water, like soda, like?
Water's water, if there's water in it, you can be, now, you could actually be thirsty and start eating fruit. The fruit contains water, it'll take a while, because it doesn't have as much as a few sips, but you can satisfy. Water's water, doesn't matter where it comes from. Pardon?
I said watermelon.
Watermelon has lots of water, yes. Okay, so we're looking just at water, no matter where it comes from, because we saw it comes from ingestion. Whether that's water or it's brought in with whatever you ate. Some foods have a lot of water, watermelon. Some foods don't have much water, grains. They're dried. Okay, you drink enough water until the solute concentration and blood pressure have been brought back to normal. If you did not drink enough, then these will still be going on and you'll feel thirsty again. Now, why do you just drink a little bit? Because the problem is the water. You want to get enough, but not too much. When you feel thirsty, don't drink a gallon, because now what do you have to do? Get rid of that. So the way our body is built, drink a little bit, see if it's enough. Not enough, drink some more. Enough, don't drink anymore. See, the thirst regulates. That's the body's response, that when we don't have enough water, is to get some water. Now, behind the scenes, what is your body doing? What's going on besides thirst for water balance? Remember, we're talking about water loss. What is your body gonna do? Cut this down. ADH is gonna be produced, aldosterone is gonna be produced, and they're going to reduce water loss. Okay? You may be down, let's say you're down 200 milliliters of water. You may only have to drink 100 because you can save 100 right here. There we are. Your body does both at the same time. Make you thirsty and conserve water here. See how this works? This is why this chapter follows the kidney. Can you regulate water loss? You can, but it takes work. Okay, water is lost through the skin and the respiratory structures, and that is called insensible water loss. Why is it insensible? You're not aware of that water loss. You're just not aware of that water loss. Sensible water loss is perspiration. You're aware of it going onto your skin. It can become substantial if it is a hot day and you're working hard. If it's hot and you're doing a lot of physical work, you're going to sweat a lot. You can lose several liters an hour. Now, to replace that, you're going to be drinking several liters an hour. Okay? Now, remember that in the background, regulating water loss is our kidneys. We already said that. And the kidneys are regulating the composition and the volume, but we're concerned about the volume. When they increase the volume, we know the composition is going to become dilute. When they conserving water, the concentration goes up. Okay? Learned behavior can help reduce water loss. What kind of learned behavior do we have? I mean, if you start working, doing some yard work, and it's 65, 70 degrees, are you losing much water? No. Now it's up to 95. Are you usually losing a lot of water? Yeah, you can actually go inside at that time and stop working until another cool day. Get the picture? Learned behavior can help reduce water loss. Okay. Does your body regulate the osmolarity of those fluid compartments? Yes. How does it do it? By regulating water. That's essentially how it does it. Okay? Altering water content of a solution will change its osmolarity. You lose water, osmolarity goes up. drink too much water, osmolarity goes down. Simple relationship. An increase in osmolarity of the extracellular fluid will increase thirst. Water that you drink will enter the ECF, okay? ADH is also going to happen at the same time as thirst, and it's going to reduce water loss. If you have a decrease in osmolarity, you've been drinking too many fluids. 16 beers, probably gonna decrease your osmolarity, okay? I'm just drawing a number out of a hat, okay? That, once you have decreased your osmolarity, you have no thirst at all. Your blood pressure's up, nothing is going to stimulate thirst, okay? And this decrease in osmolarity, of course, is going to inhibit ADH secretion. You're gonna have a lot of water lost in your urine. And where is it gonna come from? Directly from the extracellular fluid that got it. So, decrease osmolarity, too much water in your interstitial fluid. You're going to lose it right here in the urine. And you definitely won't be thirsty. Okay? That's a simple relationship. There is something else that we need to say, is you can be drinking alcoholic beverages, and yes, that fluid is going to cause you to increase urine volume, but what does alcohol do to ADH? It suppresses it. So if you're drinking concentrated alcohol, you're not getting a lot of liquid, right? So it's going to decrease ADH, and you're going to lose a lot of water. So if you're drinking shots, you're going to be thirsty. Drinking a bunch of beer, you're going to be losing a lot of, and you won't be thirsty. It's just the nature. So remember, alcohol itself will repress or inhibit ADH secretion, which means you're going to have a large volume of urine. Just little facts. Regulation of the volume of the ECF. If the EC volume increases, it will increase blood pressure. So when we're talking about the ECF volume, that's plasma and interstitial fluid. When you increase the volume of extracellular fluid, you're going to increase plasma volume, increase blood pressure. That's going to happen. So understand those are there. So if you ever increase the ECF volume, we have 4 mechanisms. We've already discussed them several times. If you have ECF volume going up too high, there are 4 mechanisms to reduce ECF volume, okay? They usually work together. Remember those baroreceptors? If you have an increased blood pressure, we're going to have a reduced sympathetic stimulation of the afferent arterioles. What's going to happen to GFR? It's going to go up. So if we have reduced stimulation of those smooth muscles, they relax, increase the capillary hydrostatic pressure, and we're going to increase GFR, which directly increases urine volume. Now, if blood pressure ever falls, blood volume falls, blood pressure falls, then we're going to have a decreased blood pressure. We're going to have increased sympathetic stimulation. So for increased blood pressure, there it is. If it falls, the reverse is going to happen. Increased blood pressure, increased sympathetic stimulation, reduced GFR, reduced urine volume. Okay? So baroreceptors are one of the 4 mechanisms that regulate ECF volume. Okay? Next, the juxtaglomerular apparatus. If blood volume drops, what happened to blood pressure? Drops. You'll get renin released, angiotensin produced. It's going to cause aldosterone release, increased sodium and water recovery in the distal convoluted tubule, and we're going to have vasoconstriction also occurring. The reverse occurs if blood pressure rises. Will you get any renin released if blood pressure rises? No. Blood pressure goes up, no renin release. Renin's only released when it drops. So you won't have any angiotensin II, you'll have no vasoconstriction, and you're going to have no aldosterone, no sodium and water recovery from aldosterone. You've heard of all three of these. You know exactly what's gonna happen. If your blood pressure increases, okay, we're gonna have atrial natriuretic hormone or atrial natriuretic peptide, both, released, reduces sodium and water recovery directly. It's gonna suppress ADH, but it's not here on this part. We covered a little more there. And which is going to cause a reduced water reabsorption, increases the volume of urine. But where did we start with? Blood pressure too high because blood volume's too high. And ANH is going to reduce sodium and water secretion and increase the volume of urine. You're losing water from that blood volume and gonna eventually decrease blood pressure. If your blood pressure is too low, we know that we're gonna have ADH release. This can be direct, but it's usually happens before this by the osmolarity. Causes increased water recovery in the nephron, reduced fluid volume. So the four mechanisms that regulate the ECF volume, they don't all work at the same time, do they? No, because this one is when we have increased blood pressure or decreased. This one is only for decreased blood pressure. This one's only for increased blood pressure, and this is only when low blood pressure. So there's only one that works all the time. That is the baroreceptors. Excuse me. Okay? You know these, all we did was put them together into one slide talking about ECF volume. Why do we talk about the ECF volume? Because that affects directly blood pressure. ECF volume and blood pressure are directly related. Volume goes up, blood pressure goes up. Volume goes down, blood pressure goes down. Okay, this is just a summary slide of things you knew all of that. None of that was new. We just drew it all together. Is the composition of the extracellular fluid or intracellular, regulating the intracellular fluid composition? That's what's next. We already saw the intracellular fluid and extracellular fluid, interstitial fluid specifically, are much different, radically different. The plasma membrane regulates the composition of what's inside the cells. Can the concentration of materials inside the cell go up and down? Yes, because water can go in or water can go out, and that changes their concentration. So given a steady state of fluid solute concentration outside of cells, it stays constant. The plasma membrane is regulated. But understand, extracellular fluid can influence the total amount of water inside the cell. The plasma membrane regulates the concentration of various solutes in there by pumps and by channels. So that's the plasma membrane forming the way I like to say it is, it keeps these solute concentrations there to make it compatible for life. If you alter it too much, we don't have a living cell anymore. Water moves across the plasma membrane simply by osmosis. The intracellular fluid inside of cells, can compensate for a loss or a gain of the ECF volume. We already talked about water moves across the plasma membrane by osmosis. There's always water channels in the plasma membrane. It needs to be there. And because the cell's making water and it's shipping water out. So if you lose water in the interstitial fluid and plasma, water will flow out of the cells. Remember, it's a bigger compartment. So it can lose a little water and makes a big difference in the ECF. Changes in the composition of the ECF will cause water to move by osmosis. Lose water out of the ECF and solutes goes up, water's gonna move out by osmosis. It's just a simple fact. Okay? Now let's go to specific electrolytes, and we're gonna go through several of them today. We may actually finish early because I don't have part 2 ready, which is no big deal. I'll have it ready for Thursday. I did not have time to do it this weekend. I was engaged in other activities with family. was a nice one. Okay. The concentrations of various ions in the ECF is regulated. Is there regulation going on for the ions inside of a cell? Yes, that's the cell regulating itself. Okay? We're talking about your body regulating individual electrolyte levels in the extracellular fluid, the fluid outside of cells and inside of the cells. Now, understand for most of these electrolytes, only proteins are different. Except for proteins, those electrolytes are in equilibrium between the two. So we can talk about it in plasma, we can talk about it in the interstitial fluid, but really they're like one compartment as far as ions go, because ions can go right through, across the plasma membrane, or we go through between cells easily. Okay. The dominant cation in the extracellular fluid is, as we saw, is sodium. Sodium is 90 to 95% of all the cations in the extracellular fluid. 90 to 90, you just have to go back to that table. It's 100, what was that number? 150, 140, something like that. And all the rest are much, much smaller, okay? The dominant cation, the vast majority of cations in the extracellular fluid is going to be sodium ions. We are salty individuals. Guess what the dominant anion is in the extracellular fluid? Chloride. So, yeah, that's the major cation and anion in the extracellular fluid. Which means if that's the major cation and chloride's the major anion, the vast majority, the osmolarity is due to those two ions. 90 to 95% of all the cations are sodium. 90 to 95% of all the anions are sodium, are chloride. Each one accounts for nearly half of the ion concentration that produces the osmotic pressures we see in various compartments. Okay? So 90 to 95% of the cations are sodium, and 90 to 95% of the anions are chloride. That means each one is nearly half, responsible for nearly half of the osmotic pressure of the ECF. Okay? So you can't change the concentration too much without affecting the osmotic concentrations and the osmolarity and the ability of fluids to flow by sodium. If we lose a lot of sodium ions, say suddenly your kidneys are not recovering much sodium, what's going to happen to the sodium ion concentration in your extracellular fluid? If you're losing a bunch, it's going to go down. What's going to happen compared to cells? The water concentration is now higher in the fluid, in your extracellular fluid, than in the cells. The water concentration is higher, and it's going to go into cells. So we have to maintain this sodium and the chloride at high levels so that we can balance the water content of the two compartments. You lose a lot of sodium, boom, water comes out of cells. Gain too much sodium, water goes into cells. No, gain, water comes out, lose, it goes into cells. There I got it straight. Now, most people consume too much sodium, which means we're all the time losing sodium, okay? There's a reason we like food lightly salted. Why? We need the sodium. We have to take a certain quantity of sodium ions in. Back in chapter 25, where we looked at ions and bringing them in, you had to take in 3 grams of salt a day. That's a lot of salt, okay? And why do we need that? Because we're losing it all the time, okay? Most people consume too much sodium, is no problem there. Now, can eating too much sodium ever be a problem in some people? Yes. If they have high blood pressure, then they're going to have too much sodium causing problems, increased blood pressure. So they have problem regulating the sodium, reduce your sodium intake. If you don't have problems with high blood pressure, you don't have to worry about it. You really don't. Only if you got high blood pressure, because you don't want to be forcing more fluid into your bloodstream. Aldosterone increases sodium resorption, and when absent, the sodium is going to be excreted, okay? Sodium levels are regulated by regulating. We don't regulate sodium concentration directly. What we do is regulate the ECF osmolarity and blood pressure. Yes,
I'm sorry, in the past slide, did you say excreted or secreted?
secreted,
Oh, secreted.
excreted. It's gonna be excreted when it's secreted. It's gonna be excreted when it's secreted. Yes. Okay, sodium levels. We don't regulate them directly. We regulate the extracellular fluid osmolarity, think ADH, and blood pressure. We regulate those two, which regulate sodium. As sodium levels increase, ADH is secreted. Okay? ADH is gonna be secreted. We're going to recover some water. What does that do to sodium levels? Brings it down as you recover water. Okay? If blood pressure increases, sodium and water are secreted. Okay? If blood pressure decreases, renin, angiotensin, and aldosterone lead to the conservation of sodium. So if blood pressure down, conserve sodium, that ends up conserving water, and you can lower the sodium ion concentration.
Is osmolarity and osmolality
The same.
Okay.
They're the same. I think of molarity rather than molality, so that's why I've always used molarity. A certain solution is a certain molarity, not molality, but they're identical. I've just always grown up with molar, not molal. Okay, chloride ions. It's the dominant cation, anion, in extracellular fluid. We are sodium chloride high. And there are no mechanisms that regulate chloride directly. All we do is regulate sodium, and chloride always comes along. So we just, how we regulate sodium also regulates chloride. Regulation of potassium ions. The major cation in the ICF is potassium. Remember, we need a certain amount of potassium, okay? And if you have too much potassium or too little potassium, that affects certain cells greatly. So, if you have too much calcium, hypokalemia, okay, it's going to affect electrically excitable cells. These would be muscles and neurons. So, these are the causes for having too much calcium. These are the effects. Decreased neuromuscular excitability. Pardon? I said sodium. It's potassium. Okay? Too much potassium. Hypokalemia. Okay? Decreased neuromuscular excitability. Decreased smooth muscle tone. Delayed ventricular depolarization. Skeletal muscle, smooth muscle, cardiac muscle, bradycardia, cardiac muscle. Atrioventricular block is also cardiac. So, too much potassium in your extracellular fluid has those causes and those symptoms. Too little potassium, hyperkalemia, those are the causes. Here is increased neuromuscular irritability, jumping, muscle weakness, loss of muscle tone. Again, action. Here's the only action potential, and it's happens in if it's severe, and it happens in cardiac muscle. Now, are neurons affected? Yes, but they have. When they go to affect neurons, the whole nervous system doesn't work right, and they don't have that really listed up here. We had looked at. Where is calcium involved in neurons?
No. The major use and involvement of calcium is it's potassium. It's just maintaining, the, resting membrane potential. That's the only thing there. I was thinking calcium.
Oh, it's potassium.
Yes, the potassium is used for maintaining the resting membrane potential, which they use for action potentials and gradient potentials. But when you have potassium problems, it affects neurons, but affects the nervous system in general. Doesn't produce symptoms that are, these are all muscle, those are all muscle.
Is that why sometimes you get the muscle twitches?
I don't think that potassium ion levels are causing twitches. Now, it's true when you have muscle twitch, it just does a brief little contraction. It's the neuron that has the problem, not the muscle. So there's no muscle twitches here, no muscle twitches here for symptoms, but spurious action potentials going down a somatic or autonomic motor neuron will cause twitches. Regulation of potassium ions. Potassium is absorbed in the proximal convoluted tubule, and that's obligatory, okay? And it's secreted as needed in the distal convoluted tubule and collecting things. High potassium levels and angiotensin II will stimulate aldosterone secretion and cause increased potassium excretion into urine. So when you have a high potassium level, you're going to have high angiotensin and aldosterone, and you're gonna lose a lot more potassium. Okay? Normally, we reabsorb a standard amount, obligatory amount, every time. And then, if it's too high, it's gonna be secreted. If it's too high, it's going to also cause secretion. This secretion that's talking about here is there, aldosterone stimulated. Now, normally aldosterone is secreted when? Blood pressure low, okay? But there is another stimulation for aldosterone, and that's high potassium levels. High potassium levels itself will stimulate aldosterone. Normally, you secrete some as needed. Too much potassium, you secrete more. Too little potassium, you're not gonna secrete as much. Aldosterone is the major method for removing excess potassium from your body. Okay. We have 30 seconds for one question. What effect would drinking a pitcher of distilled water have on ADH levels? Go down. Yeah. Okay. We will start here with part 2 on Thursday. Now, we will finish part 2 easily because it's a shorter section, and we will actually be able to start chapter 17 on Thursday. It will not be on the exam. I just want to fill up the rest of the time. Wait a second. I had already said that the test was going to be after, which means if we finish chapter 27 on Thursday, and we'll do chapter 17 on next Tuesday, and the exam will be the Tuesday after Thanksgiving. Okay? But chapter 17, when we start, it will not be on the exam. Okay? Just 26 and 27.